Okay, good morning. So today I will also go through what you are supposed to know from Ma3c, but from the next session we actually continue. So I am actually teaching some of the pages in the book, but I am extending it a little bit more. That's also a recap there. Okay, so if you remember, we realized that this is the definition of the derivative of a function. The limit of f of x plus h minus f of x over h when h goes to 0. But then we also learned that following this, it becomes sometimes very boring or very tedious at least. And of course, sometimes it really becomes impossible to calculate the limits. So we have to develop another way. And the other way was that we wanted to set up a table of derivatives, and then we learned that because there are infinitely many functions out there, we cannot find one single formula for every single function. So we learned that it is a good idea if we categorize them. And then in the category that we had, so we learned only two formulas. So if the function f is any sort of constant function, its derivative is 0. And we also learned another formula so that x to the power of a, whatever a is, of course, if a is not equal to 0, because if a is equal to 0, what happens? X to the power 0 becomes 1, a constant, and its derivative becomes 0. Okay? So if a is not equal to 0, then the derivative of this function becomes a x to the power of a minus 1. And I spend a lot of time to give you a lot of different examples that this formula can be useful in finding the derivative of them. So even though that is one single formula, but we were able to derive the derivative of a lot of functions using just this single formula. So what was important for us here? So let me write some of them in blue. I don't know how to write them. So the consequence of this is something that I want you to know. So first of all, x prime is what? Is 1. And then we also learn the square root of x prime, because if this is not in the formula sheet, but I really recommend you to have it in your memory. Otherwise, you have to use this over and over again to calculate the derivative of this function. If you remember, it becomes 2 square root of x. We also did this one before, so it is not bad to have this in your memory as well, so it becomes minus 1x squared. So these are special cases of that formula, but if you don't know them, in principle, you can derive them from this. For example, for this case, a is 1. For this case, what is a? What is a? 1 over 2, because we had also another formula, so let me change my color here. So we also had these formulas that I told you are important here in this topic. So a to the power of minus n is 1 over a to power n. Yes. And then we also had square root of a is a to the power of 1/2. We also had the nth root of a is a to the power of 1 over n. These I'm sure they are in the formula sheet, but I'm not sure about this, but we also need that. If you have the nth root and a to power m, then it becomes a to power m over n. So these are the formulas from the topic of powers that might be relevant in this discussion as well. Okay, these are the particular functions, but we also had 3 general rules. Do you remember what happens if I have the derivative of the sum? What happens if I have the derivative of the difference? And what happens if I have a constant number multiply the function I am interested in finding its derivative? So these are generic rules, so let me write them here. So number 1, so the first one tells you that if you have sum of 2 or more, it doesn't matter, sum of the 2 functions, and you are interested to differentiate that. So the differentiate is the word that I use for the process of finding the derivative. If you differentiate this, this becomes f prime plus g prime. Yes? What does it mean? It means that it doesn't matter if you add first and then differentiate, or differentiate first and then add. The results are the same. And the same thing for this difference, f minus g prime is f prime minus g prime. And then we have another formula that if I have a function multiplied by constant and I want to differentiate it, I don't care about the constant, I just concentrate on differentiating my function and then I multiply them. So c is a constant here, yes? I call it a multiplicative constant, but that is constant. Okay, and I emphasize that don't push this analogy further, because if you write, so let me not put any number for that. So if you write f times g prime, and you think that this is f prime times g prime, that is wrong. And we will learn, it becomes a little bit more complicated than you see, but we studied this year. Okay, and then f over g prime, if you think it is f prime over g prime, that's also wrong. The reason I write it and cross it over because I see many students make mistakes. So this is more or less the summary of what we had, with a very long example using these formulas over and over again to get used to it. Okay, any questions? Okay. So now what we want to do, there are two other formulas that in principle you should have learned in Ma3c. Okay, so I want to add them here, but there is no time if I want to go through the proof of them because the proof of them are very technical. So I just write them down here for you. Okay, so what is that? One is that what happens if I switch them? Okay, so let me, first of all, some of you might not appreciate this. So there is a very big difference between these two, even in the name. This function is called a power function. This function is called an exponential function. Okay, they are different. So when I say a power function, x to power a, it means that this is variable, this is constant. Okay, this is called a power function. Okay, the formula we learned so far on the second row only works for this case. Okay, but if I swap them, a goes down and x goes there. So what happens? This is the constant. Yes. And this is variable. And then it is not a power function, it's an exponential function. Okay. And so the formula I got there is only for a power function. So what happens if I have an exponential function? So that is also good to write it down and cross it over. So if you think a to power x prime is x a to power x minus 1, that is also wrong. Okay, so what is the correct formula? I don't know if you remember it or not. Yes, anyone? Yes?
Natural log.
Something related to natural log, but how? The formula is a to the power of x. So the function repeats itself exactly, but you need to multiply it by the natural log of the base a. Okay. You might, if you have forgotten a little bit about this natural log, might be I can find some of my past videos and put them on the Google Classroom so that you can review. But anyway, if I want to summarize what ln of a is, you remember what that is? So ln of a is called the natural log, so it is a logarithm. Okay, so it means that if I say ln of a number, this is a shorthand way of writing logarithm of a to the base e. And e is the Euler number, yes? Which is also an irrational number. It's one of the, so this and pi together are very fundamental constants in mathematics. So e is approximately 2.7, but it is also a rational number, so it continues forever. So if I choose this very particular number as my base, instead of writing this, I just write ln of a. So whatever property you have for log, you can have it for ln as well. For example, you know that logarithm of x to the base a, so let me write to the base b, it's a more natural letter. So plus the logarithm of y to the same base, what can I write? I can write log of the product to the same base. So that is one of the fundamental properties of log. Yes, if I have a log of a product, it is not log of the first one multiplied by log of the second one. It is the log of the first one plus log of the second. So these are fundamental properties of logarithms. So now this formula can also translate itself to the language of natural logarithm if I choose b to be e. Yes, if I choose b to be e, then this becomes log of x to the base e, but there is a shorthand way of writing it, so I just simply write it as ln of x. And if I choose b to be e, the next one becomes ln of y. And if I choose b to be e, the next one becomes ln of xy. So you see, this is not a new formula. Understanding what the natural logarithm is a little bit conceptual. I have it in my lectures in Ma3c, but the consequences are the same. So whatever formula you had for ln logarithm, you have it. For example, another famous formula for logarithm is what? What happens if I have the difference?
Division.
It becomes division. Yes. It becomes log of the first one divided by the second one to the same base. Now, if I want to translate it to the language of natural logarithm by choosing b to be e, this becomes ln of x minus ln of y is equal to ln of x over y. And one important formula is that, for example, log of a number a, log of a number b to its own base is what? Is 1. And now if I choose b to be e, this becomes log of e to the base e. So this means ln of e is 1. Okay? Another very important formula of log is this formula. If I have b to the power of logarithm of x to the base b, what the answer is? This is very important.
B.
No, it is x. Yes, it is x itself. Okay, if I want to translate this into the language of natural log, so let me write it here. Instead of b, I put e. So this becomes e to the power of logarithm of x to the base e, but logarithm of x to the base e is called ln of x. And this becomes x. Okay, so these are important things that you need to know about the natural logarithm. But for the case of our lesson right now, you don't need even to know, just copy and paste what you see, okay? So if I give you an exponential function and I ask you to differentiate it, this is very interesting. The function repeats itself exactly, but then you have to multiply it by ln of the base, okay? Which, of course, I think in the Ma3c, they also put a constant k there. If that happens, you also multiply it by a k, okay? But what happens for e to power x? You see, e to power x, if I ask you to differentiate this, so you can follow the same formula. You don't need any new formula. But here, a is e. Okay, so what happens? It becomes e to the power of x multiplied by ln of e. But ln of e is 1, so it becomes e to power x. Well, that's a very interesting function. It's a function whose derivative is exactly equal to itself. Okay, but in Ma3c, they have written it this form that I don't like it that much. Okay, but anyway, we learn it better this year. So this k goes down and then the function repeats itself. Okay, so if you have a constant k multiplied. So, and if you don't mind, let me just use my notation c, because in English a constant has a more natural number if I choose it with c. So I will add this one here as well. So if you don't mind, let me also add c here. The only thing that happens, c also appears here. So if you don't mind, let me write it more properly. So this c goes down. I will teach you why this c goes down. I think the only reason that they did it like this in Swedish system because they don't want to teach you more advanced topics. So and then they found that if I don't put a c there, it is very boring. So they want to give you some room to be creative a little bit. I don't know why, but anyway. So ln of a, and then here e to the power of cx, c goes down and the function repeats itself. Okay, but of course you know that an exponential function, a should be, by definition, an exponential function, a is positive and a is not equal to 1. Okay? If I don't choose a to be positive for some values of x, this function is not defined at all. For example, if a is equal to -1, x cannot be chosen to be 1 over 2. To get rid of these problems, we choose a to be greater than 0. But why do we exclude 1 from it? Because if a is 1, then 1 to power x is just simply 1. So that's a constant function. So this is why in this one, let me write it here. So a is positive and a is not equal to 1 for this case. Okay, so that is what you actually learned in Ma3c. So you had 4 formulas and these three generic rules. We discussed about these a lot, so let us solve some examples today from these two and then we continue. Okay, so example, differentiate each function, yes? So number one, so this is a good example, I would say. Let me put two functions in one function. So let me write x to power 2 plus 2 to power x. So by only the lesson of the previous session, I was not able to solve this. You can feel the difference, yes? X to the power of 2 is what we learned before, but 2 to power x is what we are learning now, yes? It is a power function, that's an exponential function. So they have different rules, not the same rules, okay? So if I want to differentiate it, let me again do it once more. You don't need to write so much, but let me just teach you how to think. So this is my goal. But I have to use which rule? This rule number 1 here. So this becomes the derivative of the first one. You don't need to write it, but you need to think in this way. Plus 2 to the power of x prime. Okay, so I'm using rule number 1. And then the derivative of this one is the second row in my table. Yes, this is this rule. But the next one is this rule. Yes, I hope that you understand the difference. So what is the derivative of x to the power of 2? Is 2x. What is the derivative of this one? The function repeats itself, but you have to multiply it by ln of 2. Yes, is that clear? Or, yeah. So for example, number 2, this is also, I think, in the book, so let me write it for you. So g of x, so let me write, for example, 2x. This is also good. So 2x to power pi plus pi to power 2x. Okay, so we want to differentiate this function. So what do you think I will do? I hope that you see the difference, yes? This one is a power function, yes? But this one is an exponential function. because pi is a constant number. Okay, but before doing that, I need to somehow solve this problem, yes? So 2x to power pi can be written as what? This means 2 to power pi, yes, multiplied by x to power pi. And then plus pi to power 2x. That's it. Okay, now I start differentiation. So what happens, so if you don't mind, let me also write this completely. So when I ask you to differentiate this, I mean differentiate this combination. Yes, that's what I mean. But there is a sum, so I have to take the derivative of the first one plus the derivative of the second one according to rule number 1. So this becomes 2 to the power of pi x to the power of pi derivative plus pi to the power of 2x derivative. Yes? Okay, but what should I do here? Which rule is needed here now?
The third.
The third one, because that's a constant multiplied by a function. So if I have a constant multiplied by a function and I want to differentiate it, I don't do anything with my multiplicative constant, so I just copy and paste it. But then I concentrate on taking the derivative of x to the power of pi. And if you don't mind, let me just copy and paste this once more so that we can do them together. Okay, so 2 to the power of pi is just 2 to the power of pi. So what can I do for this one? X to the power of phi. Is it exponential or power function? It's a power function. So if it's a power function, that's the second row. Yes, so what happens? Pi goes down, and then x becomes to the power of pi minus 1. That's what you need. You cannot simplify it more than that. And then this one is the third row. So 2 here, you see, this pi is taking the role of a, x is just x, and 2 is taking the role of that c. Yes? So if I want to differentiate it, so I need to, the function repeats itself. So first, 2 goes down, the function repeats itself, but that's not finished. I have to multiply by ln of pi. So this expression is the derivative of that function. Is that clear? Okay, so let me give you some more. I want to wait for you. You solve it. Okay, so I start writing, you can do it as I write. Okay, so number 3. So I want to wait for you so you can solve these two. Okay, so if you don't mind, let us just start solving them. Of course, the only thing that you need to learn is how to change the given function into a form that you can use the table of formulas. Okay, so that's the only thing we have to do. Okay, so I want to ask your opinion, so please talk to me so that if you're on the wrong track, I can correct you. Okay, so number 3, I want to take the derivative of this function. So what is the first thing comes in mind? Because if I am supposed to solve this derivative of this one, I have to somehow use one of these things that you see, or a combination of them. Yes? Rule. So I expand that. So yes, because I cannot immediately differentiate. Why? Because this function in its form that you see right now on the board is not in my table. Yes? So I have to change the form of it in a way that I can use these formulas. So the good starting point is to say the first one squared plus 2 times the first one times the second one, and plus the second one squared. Yes? And now what is the first one? So you know this rule. If you have forgotten, let me remind you. If I have, it's of course in the formula sheet, but at this level I think you should have it in your mind. Yes. So a to power x raised to another power. What is the rule? I write x times y. So let's do it. Okay. So what I do here, this is one exponent. I am raising it to another exponent. So I repeat the base and I multiply the exponent. So it becomes 2x. But what happens here? E to power x times e to power minus x
1.
is 1. Yes, because e to power x times e to power minus x, the bases are the same, and I add the exponents. But when I add the exponents, it becomes 0. E to power 0 is 1. So this becomes just simply 2. And for the same reason, this becomes e to power minus 2x. So now, is it ready to differentiate? Yes, because it is a sum of some functions that are in my table. Yes? So now I start differentiation. So this differentiation cannot be started immediately. So I say h prime of x is equal to the derivative of the first one. What is the rule? This constant goes down, the function repeats itself. The derivative of 2 is simply 0, and here minus 2 goes down, and the function repeats itself. So that's the answer. Yes? Is that clear? Okay, and now, but what about the next one? So let us write the next one as well here. So number 4, do you have any idea what to do with number 4? So this is not in my table because I do not have 1 over an exponential. I have the exponential itself. So yeah, just say it. What should I do?
E to power minus
3. So that is easy, yes? So I bring it up and make it with negative exponent. So it becomes, so I would write it as k of x is equal to e to the power of minus 3x. That is the first step. What about the next part? What do you think I will do?
expand.
Expand, yes? So I copy and paste e to power x, and then I start expanding. But because you learned expanding here, let me just do it faster. The first one squared becomes what?
E to power 6x.
E to power 6x. And 2 times the first one times the second one is 2e to the power of 3x, and finally the second one squared. Yes? So still one more step is needed so that I can start differentiation. Why? Because here you see a product, but you haven't studied the product rule yet. So you have to get rid of any products that you need. So I will continue one step more. So it becomes e to the power of minus 3x. So let us multiply this in our head. If I multiply this there, what happens? E to power x times e to power 6x, it becomes e to power 7x. The next one becomes 2e to the power of 4x, and finally e to power x. Everything ready now, yes? Because I have a combination of those bunch of functions that I know how to differentiate. So k prime of x is equal to, here minus 3 goes down, e to the power of function repeats itself. Here 7 goes down, the function repeats itself. Here 4 goes down, but there is also a 2 there, so they will be multiplied, it becomes 8, and the function repeats itself. And here e to power x, the derivative is e to power x itself. So it doesn't hurt if I write a special case here as well. So if you want, you can, I want you to see that. So the derivative of e to power x is just simply e to power x. The derivative of e to power minus x is minus e to power minus x, because in this case c is minus 1. Minus 1 goes down. Okay? So these are special cases of that form. So that's the answer. Is that clear? Okay, now the next one. You should in principle have a little bit of experience of what to do with these type of functions. These are fractions. In general, we still haven't learned how to differentiate fractions, except that we have one single item in the denominator. Do you remember we had some kind of these questions in the previous lesson? So what do you think I will do here now? Because in this form, I cannot differentiate. This is not in my table. What do you think I will do? Yeah, I will separate them. So do you remember I wrote something like that in the previous lesson? So if you have a plus or minus b plus or minus c plus or minus etc. divided by d, you can write a over d separately plus or minus b over d plus or minus c over d plus or minus, yes? So that's the idea I will use here. So remember this trick whenever you have a fraction and you have one single item in the denominator. Even if in the future you learn about this quotient rule, but this method will be easier to do. Okay, so this is why I'm really advising you to have this idea in mind. Okay, so the first thing that I will do, I will rewrite L of x like this. 2 to the power of x divided by 5 to the power x. Yes, and then plus 3 to the power of 2x divided by 5 to the power of x. And then finally minus e squared, which is just a single number, divided by 5 to the power of x. Okay, so you have to be a little bit more creative here as well. So you cannot start doing this part immediately because this is still a quotient. So how can I get rid of being quotient? But the good news is that the exponents are the same. Do you remember a formula from Ma3c? If I have a to power x divided by b to the power of x. So I have two powers for which the exponents are the same. So I am allowed to do what? I am allowed to divide these and put one single exponent for the whole thing. Yes? So these are extremely important formulas. I hope that you haven't forgotten them. Okay? Have you seen that before? Yes. This is Ma3c, by the way. You have probably studied that in Grund School as well. Okay. So why do you know that? For example, if I say 2 to the power 2 over 3 to the power of 2, how do you do that? Yeah, so this is this you say 2 to power 2 divided by 3 to power 2. So it means that sometimes you need to go in that direction, sometimes you need to go in this direction. Yes? So that's exactly what I want to do. So what can I write? I write 2 over 5 to the power of x. Okay, but now here the problem is that this is 2x, this is x. How can I solve the problem? Yes? 9. Yes, because 3 to the power of 2x can be written as 3 to power 2 and then to power x, but the good news is that 3 to power 2 is just simply 9, so I can write 9 to power x. So this becomes 9 to power x, and then the same story. So what can I write? I can write what? 9 over 5 to the power of x. Yes? Is that understandable? So I wrote this in that. So what can I do here? Yes, so it becomes e squared is just simple a fantasy number here, and then I bring it up, so it becomes 5 to the power of minus x. So this is what we are supposed to do. Okay, so now everything is ready. So L prime of x is equal to. So what is the name of this function? This is an exponential function. Why? Because the base is a constant and the exponent is variable. That's also an exponential function. This is a constant multiplied by an exponential function. So everything is ready. So what should I do? I need to take the derivative of this one plus the derivative of this one minus, I don't do anything with the multiplicative constant, I take the derivative of the last one and multiply it. So which formula is needed for taking the derivative of this one? The third row, yes? So if you compare this with the third row, yes, I'm just talking about 2/5 to the power of x. So can you tell me what is playing the role of this a in that problem? 2 over 5. So what is c in that problem? 1. And x is just x. So this is playing the role of my a. So then if I want to differentiate it, according to the differentiation rule, number 1 should go down, so it doesn't have any effect. So then it means that the function repeats itself, but you have to multiply by ln of 2/5. That's it. You don't need to do anything. You just write it like that. And the next one is also similar. So it becomes the function repeats itself, and then ln of 9/5. But here, this is a constant multiplied. So when I want to differentiate, I don't care about the constant. I concentrate on differentiating this. But this c is not 1, the c is -1 here. Yeah, so -1 goes down, so it becomes plus, and then the function repeats itself, and then multiplied by ln of 5. So that is the derivative of this function. Is that clear? Okay. So now the next one. So the next one, what do you think I will do? Expand, yes, because that's a product. We don't know how to use the product rule, so we have to expand. So u of x, I will expand that. So this becomes 2 to the power of x multiplied by the first one squared. What's the answer? The first one is squared. This one is squared. So I will write it down here if you're a little bit doubtful. This one squared. According to this rule that you see on the board, I will copy and paste the base, but I multiply these two numbers, x times minus x over 2. But these 2 and that 2 are cancelled, so what is left is minus x. So the first one squared is 3 to the power of minus x. And 2 times the first one times the second one. Okay, so what can I do? Just write it down. So 2 times the first one times the second one, and plus the second one to the power of 2, which is 5 to the power of 2. Yes? Yes?
For the previous question, isn't it supposed to be minus c squared?
No, this -1 goes down. Yes? So here, this c goes down. In this case, c is -1. So when it goes down, it makes that negative to positive. Yes? Okay, now I multiply this in. So it becomes 2 to the power x multiplied by 3 to the power of minus x. The next one is, there is a 2 here. I multiply this in, 2 to the power x multiplied by 3 to the power of minus x over 2. And then I multiply this by 5 to the power of x. And then I multiply this in again. So 2 to the power x multiplied by 5 to the power of 2x. Yes? Okay, then what? This is not good yet because I have a lot of products. We don't know the rule for the product. So what do you think I will do here? I think it's very simple now, yes? So how can I write this?
2x over 3x.
Yes, 2x over 3x. Yes? So do you mind if I write it in one go 2/3 to the power of x? Is that understandable for everyone? Because 3 to the power, so 2x, 3 to the power of minus x goes down. And then I will use the same idea that I had here and I'll write it like this. Okay, but this is a little bit more tricky. So what should I do here? First of all, this one multiplied by that one, do you know that? What is this?
10 to the power x.
10, because these powers are the same, so I write the same power, I multiply them. So it becomes 10 to the power x. Okay? But what can I do for this one? So 3 to the power of minus, so let me write it where? So let me write it here. Okay, so 3 to the power of minus x to the over 2. So can I write it as 1 over 3 to the power of x over 2?
Yes.
But x over 2 is not good because I want to have x so that I can combine them. Okay, so this motivates me to write it as 3 to the power of 1/2 to the power of x. Is that right? But 3 to the power of 1/2 has another name. It's square root of 3 to the power of x. Okay, so everything is ready. So this 2 is just 2. But can you now tell me what can I write instead of whole this package as I told you before?
10
root of to the power of x, which I can write 10 over square root of 3 to the power of x. Yes? And then what can I write for the next one in your head? Can you do that? Because this is unfortunately x, that is 2x, so you cannot combine them immediately, but 5 to the power of 2x can be written as 25 to the power of x. But 25 to the power of x multiplied by 2 to the power of x becomes 50 to the power of x. So is everything ready now? Yes. So we can differentiate. So that was a little bit harder question. So I tried to find some way to keep you busy. But now you understand what's going on. Okay. So then everything is ready. So we differentiate. Yeah. Don't worry about the last question. You will not probably get such a question. But I want to. You feel that you know more than what you think, yes? So even with this very simple formula, you see we can solve a lot of functions. Yeah? We can still differentiate a lot of functions. So let me now finalize this. So u prime of x, and I wait for you if you don't understand. I will repeat it itself. So this is an exponential function. So the function repeats itself, but I have to multiply it by ln of the base. So it becomes 2/3 to the power of x, ln of the base. And then plus, this one is a multiplicative constant, so I don't bother about that, so I just write it. And then that's also an exponential function, so the function repeats itself. And then I have to multiply by ln of 10 over square root of 3. And finally, the last one, function repeats itself. I have to multiply by ln of 50. So that's the derivative. Yes? Okay. So now, any questions here? Are you happy with what I have done here? If not, review it a little bit. You can understand that. And if you couldn't understand, don't worry. It's probably a little bit more complicated function that I was expecting to see if you can solve harder problems or not. Okay, but now there are some things that I want you to know. First of all, the symbols and notations. Okay, so if I have a function, y equals to f of x, sometimes people say f prime of x. Sometimes people say y prime. Sometimes people write a capital D and then put f of x in front. And sometimes they use this Leibniz notation dy dx. Okay, I want you to understand that all these symbols means derivative, but all of them are being used, okay? Is that clear? But I want to talk a little bit about the Leibniz notation so that you understand why this is good to have. Because sometimes I have a function like this, f of x equals to, let me give you a simple example. So I would write a squared x cubed. Okay, so if you don't mind, let me write it y equals to this. Of course, if in the exam I ask you to differentiate it, okay, I want to hear from you. What is the derivative of this function that you see on the
3a squared.
Yeah, so you told me you thought that a squared is a constant, yes? And then if it is a constant, so it is a multiplicative constant, so you didn't touch it and you differentiated this part, so it becomes 3x squared, and you told me 3a squared x squared. Okay, this is by default correct, because usually I will consider x as variable in a function, and if there are other letters in the function, we consider them constant, even if I don't say anything. That's by default. But to be honest, I don't know who has promoted x in mathematics, but x and a are English letters, so in principle a should be promoted because it comes first. But anyway, so sometimes I really want to differentiate the function, but I want to give the role of the variable to a. In that case, Leibniz notation is useful. So in this function, they can in principle ask you to find dy dx, or they can ask you to calculate dy dA. Okay? So dy dx is what you told me. It means that you differentiate, consider x as the variable. Anything else is assumed to be a constant. So what you told me is the answer to this part. of course, all the time, by default, if I don't mention it, I mean this, okay? But if I insist to ask you about this, I want you to know that if you really know what is the meaning of the Leibniz notation, this tells you differentiate this again, but now give the role of variable to A, not X. So if you give the role of variable to A, it means the other letter, which is X, should be considered constant. Yes?
But can't they do the same thing with f prime of a?
No, f prime of A has a very different meaning. I will tell you what this is. So let us finish this. So what happens here?
2a.
So it means that you consider X as constant. When X is considered constant, of course, X cubed is also one constant. So that is a constant, but this is my variable, okay? So this is playing the role of X in principle. So what happens to A, yes? And then multiplied by my constant. And you see the answers are different. So I want you to understand this Leibniz notation, okay? So now what your question was f prime of A, that's also I want to just give an example. What is the meaning of f prime of A? F prime of A means that you have a function. When you say f prime of A, it means that you differentiate the function first and then replace every x in the derivative with A. Okay, so this is a good thing. So let us just give an example like this. So, for example, if I give you the function f of x equals to x squared plus 5x, let me keep it simple, minus 4. And then I ask you calculate f prime of a number, not f prime of x. So I say f prime of 2, for example. What does this mean? This doesn't mean that replace x with 2 and then differentiate. This means differentiate first and then replace x with 2. Okay, so let me write f prime of A means differentiate first. If you think that you might confuse, write it down somewhere. So differentiate f first and then replace the variable, which is usually x, with A. Okay, so that's the meaning of this symbol. So here, if I give you a function and I ask you to calculate this, one way of it was what? To use this limit. Okay, but that is very lengthy. We don't need to do that. We just differentiate it. So do it quickly in your head. What is that? It's 2x, and this one is 5. The other one is. And then when you have differentiated, this means that go and replace x with this number. So this becomes 2 times 2 plus 5, so it becomes 9. Okay, so that is why, so in principle, you remember I told you that f is a function, is like a black box. You send x in. The function gives you, takes that input from you, squares that, multiplies that by 5, add them, and subtract 1 from it. Okay? You can visualize f prime as another function. Okay? So f prime is a new function, but the role is changed. When you send any input x in, the derivative will multiply it by 2, add 5 to it, and gives it back to it. Okay? So this is a function. So if I don't write it f prime, I could have written it g, and then you would assume that this is a new function. But what is the relation between this new function and that function? That is the differentiation process. So differentiation is also a way to derive new functions, and that's the reason which is called derivative. This function is a function, but we derive it from another function. We call it derivative. Yes. Okay. So this is also very important to know. So if you let me solve some of the questions. Before going to the examples in the book, let me also talk about higher order derivatives. You also have learned that in Ma3c. When I say the second derivative or the third derivative, what do I mean? The first derivative, this is called the first derivative. When I say the second derivative, it means that do this process 2 times. Differentiate, you get f prime. Differentiate the new f prime once more as if it is a new function. What you get is the second order derivative. If you differentiate that one once more, it will be the third order derivative. Okay, so here in this case, if I ask you, what is f double prime? What is the answer in this function? 2. And what is the third order derivative?
0, 0,
And what is the rest of it?
0.
Is 0. This is a simple case, but there is no guarantee that I can find a formula for any order derivative so simply. Okay? So, and then the notation that we use, prime, double prime, triple prime. Is it triple or triple? Triple? Are you sure?
Yeah.
Okay, so triple prime. I always confuse this. Okay, triple prime, triple prime. And then after the fourth derivative, you don't put these primes all the way. You just write 4. But of course, this will be confused with power. So then you put it in a pair of brackets. So when you see f to the power 4 inside a pair of brackets, that doesn't mean f to power 4. It means the fourth order derivative of the function. Okay? So when I say the nth order derivative, this one. In this language, if you see this means the derivative itself, the function itself, because I haven't even started differentiation. Okay? So these are the symbols that we use. Let me also talk about these symbols. That's also a little bit strange. If I want to have second derivative, the symbol is sometimes this, sometimes this. In this case, you don't need to put any power. You just write d2 f of x. Okay? But this is a little bit unusual. I don't have time to talk about why, but this symbol is d2y and then dx2. Okay, so this is the way that people write it, okay? There is a reason to that, but unfortunately we don't have time, so let us accept it. So if I want to write the third order derivative in this language, it is this. This is the symbol here. This is the d3. And here, what should I write? d3y dx3. Okay, so these are the symbols. So the Leibniz notation, these are just symbols. There is no concept in that. Okay. Is that clear? Okay, so now we also have the notion of the second derivative and its notations. I think it's time now to solve some problems. I think, let me see if I have forgotten anything here. No, I don't think I have done some. Yes, everything is more or less done. So let us try to, first of all, I want to teach you how to use GeoGebra to differentiate. So what's, okay, so yes. In GeoGebra, if you want to do the derivative things, I think it's preferable to go to cast view, okay, if you want to exact values. Okay, of course, this is the way I do it. It might not be that effective. If you find another way, you can come here and present your way to the students as well. So let me, if you don't mind, get rid of this graphic view. We don't need it. So this symbol that you see on top is derivative, okay? So as far as I learned, in cast view, if you want to calculate the derivative, you don't need to write f of x equals 2 or y equals 2. You just type in your function, okay, without the nuances. For example, let us see what we have here on the board. For example, let us put this in, okay, and I ask GeoGebra to differentiate this. So here I have, so I don't put h of x or y, I just open a pair of brackets. And then e, it is important to use this button here. Okay, so I don't know if you just type e, it works, because you see when I put e here, the italic form is gone. So it recognizes which e is that. Okay, it's not a variable. It is the e, which is the Euler number. And then I raise it to power x. Okay, and then plus, again, I press this button, e to the power of minus x. Okay, and then to the power of 2.
That was my function. And then after that is finished, I just press F prime. Okay, that's the answer. Of course, this answer, because I understand why GeoGebra provides this answer seems to be a little bit different from my answer, but they are the same. I don't know how we can, I think we can, this one is expand, if I am right. Of course, this answer is correct. You don't need to do anything. That's the, but that's not my answer. I don't know. I cleaned my answer. So do you have my answer in front of you? So let me see if it works or not. Yes. I don't know if that was my answer or not. Yeah, that was my answer mainly. Yes, it's minus 2e to the power of minus 2x and plus 2e to the power of x. The problem is that it doesn't exactly give the human way of writing, but the good news is that it doesn't give you something wrong. Okay? So if you are supposed to calculate derivative using GeoGebra, as soon as you type the correct function in and you know what to do, the answer is definitely a correct answer. Okay, even if the answer is different. Of course, in every case, you should be able to convince yourself, if you want to, that the answer provided by GeoGebra is the answer that you got. Okay, but that is something else. So this is why we want to differentiate. But let us say I want to differentiate to higher orders. Okay, so I don't know, you can press this probably button over and over again. So yes, so for example here, I press it once more, so I get this one. I press it once more, I get another one. Yes, this is one way of doing it, which is not very reliable. I would prefer to do it, I would prefer to write the derivative itself. So you see, I write derivative, and then this comes in, and this is what you want to choose. Derivative, expression, variable, number. This is a little bit misleading. I was also confused myself. This number is not that number that you put in for x. Is the number of derivatives that you are interested in. Okay, so for example, let me take this one. For expression, so if you don't mind, let me write that function. What was that? Unfortunately, I cleaned that. So x to the power of 2, and then, x to the power of 2, and then I go plus 2x, yes, and then minus 5, something like that. And then what is my variable here? My variable is x. Now I want to take two derivatives, okay, so I put 2 here. Unfortunately, there is no way that I can make it bigger. After I press enter, it becomes bigger. So hopefully you can see what is going on, okay? Is that clear? So I put my function without any y or whatever. I just put the expression in. I introduce a variable, and the number that I put at the end is how many times I want to differentiate. So here, I want to differentiate 2 times. Can you do it in your head before I see the answer? The first time it becomes 2x plus 2, and the second one becomes 2. So if we have done it right, hopefully it gives you 2. So that number for me is very misleading, because I was thinking that number is this number, because when I say f prime of 1, I was thinking that, okay, I write x squared plus 2x, and then I write x, and then I write 1. But this doesn't mean this. It means take the derivative of this once. But if I want to calculate this, I couldn't find any very good way. This is why I'm asking you. I found it this way. So if I want to calculate f prime of 1, okay, can you do it in your head? What is f prime of 1? What is f prime of 1? You take the derivative, it becomes 2x plus 2. And then replace x with 1, becomes 4. So the answer to this is 4. The way that I understood how to do it, this was the way that I did it. So I typed the function f here. You can check it online yourself. So f of x is equal to, but I don't put equal to, I put semicolon equal to. Okay, semicolon equals to means I am defining my function. So what is my function? My function is x to the power of 2, and then I have plus 2x. Yes? And then I press enter. This is my function now. Okay, so semicolon is crucial here. And then what I do, I just type f and put this, I don't know, on my keyboard it is here, so you need to find this character. Yes, I don't know, it's apostrophe or something like apostrophe s, and then you open the pair of brackets, and inside the pair of brackets you type 1. So this is f prime of 1. Okay, if you have already defined f, and the answer is 4. Okay, this is the way I found it. That's up to you. Of course, might be you can also use this feature, because that feature is substitution. Okay, so for example, I want to calculate this derivative when x is 1. What do? I go here probably, I choose this one, and I go to this button. Yes, this button that you see, I press it, it doesn't work. Yes, so in that way it doesn't work. I don't know why. Because this will substitute in principle. Okay, because I have 2 of them, it doesn't know which one I have. So I highlight this one, hopefully it will work. Nah, I don't understand. So this, I don't know why this is coming in front of me, it's killing me. Anyway, so let us test it once more. I choose one of them, and then I press here. No, it doesn't work, I don't know why. It is saying something. Okay, so anyway, so this is the way I found it. Might be you can find another way. So be careful. If you want to use this feature, if you just write f of x equals to, it doesn't work. You have to put semicolon equals to, then type this one. It gives you the number that you are interested in. Any questions? Okay. So that was the derivative, and then, so you see there are some, so the lesson is finished until the end. I will not have time to do these 2 level 3 problems. They are hard questions. Okay, I will do it next time. But before I do it, I want you to do it yourself, at least try to think about it. So, I mean, if you want to get an A or a B in this course, you should be able to analyze such a problem yourself. Okay, so these problem 3129 and 3130, these are good problems. Okay, but let us now review some of the previous questions here. Okay, and then I want to draw your attention to this. You see this question in the book, you might see it in the national exam as well. If I ask you calculate f prime of 1 when f of x is equal to this, it's an E-level question in Ma3c. You can do it in your head, by the way. What is f prime of x? It's 2x minus 3, and then replace x with 1. So it becomes 2 minus 3 minus 1. But if you write this answer for these kind of problems in the national exam, even though your final answer is correct, you will get 0 point, because they have mentioned use the definition of the derivative. So the definition of the derivative means that limit. Okay? So pay attention. If derivative definition, or sometimes I think in English translation, if you receive the English one, if you want to, then might be they say from the first principles or something like that. When they say this, even if you calculate it correctly, you will not get any points. Okay, so let us do one exercise, because the exercises are not that hard, except those ones that I showed you. Okay, so let me go to the next one and solve one problem for you, and then we are done. I want to solve this problem. It is a very, I don't know, it's a level 2 problem, but it is not a hard one. Okay, so the curve y equals to 5x squared plus 5x has a tangent at this point. Determine the tangent, the equation of the tangent line. It's a very standard problem, but you need to be able to solve it. Okay, so I will solve it here on the board, and then we are finished. Okay, so what is my function? My function is y equals to 5x squared plus what? Plus 5x. And the point is given to you. What is that point? Minus 1 and 0. Yes? First of all, do you agree that this point is on this curve or not? How do you know that? No, how do you know? Yes, I agree with you. But how do you know that the designer of the question didn't make any mistakes? Do you really see that this point lies on this curve or not? How do you know that? You replace x with the x coordinate and replace y with the y coordinate. If this is a true equality, then that is on the curve. It is not, it is not. But it is, yes. If I put minus 1 here, it becomes 5. Minus 5 is 0. So yes, this point is on. So if you want to solve this problem, this is a very simple problem, but it is an archetypical problem. So you need to know exactly what to do. So to find an equation for the line, do you remember we talked about y minus y node is equal to k x minus x node? Okay, this is the formula which is in the formula sheet. I want to use it. Some of you might still prefer to write it like this. That is also working, but because this formula is in the formula sheet, it's better to learn how to use it. So here, what should I replace? What should I put for y0?
0.
The y coordinate of one of the points. I do not have access to any other point except this point. So y minus 0. And then the k value is still missing, but x minus 1. Yes? But the k value, what is k value? K value is the derivative at which point? At the x coordinate of the point of tangency. So in this case, it should be a y prime at minus 1. But I just told you y prime of minus 1 means first differentiate, which becomes 10x plus 5. And then replace x with minus 1. So this then means that the k value is 10 times minus 1 plus 5, which is minus 5. Yes? And then that's it. Put the numbers in. So this is minus 5, so I put the numbers in. Y minus 0 is just 1, is y minus 5 times x plus 1. And if you want, I can multiply this in. It becomes minus 5x minus. So this is a very standard problem. So you might see the same questions. If they want to make this question harder, they can just play around with this function so that you see that you can differentiate properly. Because to find the k value, you have to differentiate. So you have to know how to differentiate. If this function is complicated, the differentiation process is complicated. But the format of the problem remains the same. So is that clear? Okay, so I think we can stop here. But from the next lesson, of course, I will solve some of these hard problems here for you. The recap of Ma3c is finished, and we continue to what is really in Ma4.